Good morning. My name is Kevin Lee. I'm a senior product manager at AWS. I've been with the AWS for 7 years, and I'll let Sam introduce himself.
Good morning, everybody. My name is Samuel Weymouth. I am a specialist in security and compliance based in EMEA, UK, but I'm from New Zealand, and my other job is working for His Majesty the King and the Royal Signals as part of the Joint Cyber Unit Reserve in the British Army. So it's a pleasure having you here today. Who's got a first hand? Is this your first reInvent? Put a hand up if you don't mind. Get a few. Whoa, that's a lot of you. Anyone got more than 7 reInvents? I see a man there. I have the matching T-shirt, so 2017 is a vintage year. Thank you for attending. It's a lot of queuing and a lot of queuing and a lot of queuing that you have done. So hats off for being here at Friday morning.
Cool. Welcome to our session at SEC218, how the KMS over the year has evolved to earn customers' trust. So today's agenda, we'll look into how the KMS service evolved over the years from the product lens perspective. And next, we'll cover what it means to be having control versus having ownership of your encryption keys, how they differ, and how KMS offers you choice on this matter. In the second half of this presentation, we'll cover how the encryption and authorization work together to solve digital sovereignty use cases. And then we'll cover our new partition, the European Sovereign Cloud. So I'd like to begin with a short history lesson as to why KMS was needed back then. And to do that, we need to go back to the state of the world 10 years ago. At the time, cloud computing was gaining momentum, and regulated industries such as financial services, government, and healthcare was busy migrating into the cloud. As these industries start migrating their workload into the cloud, customers were busy trying to analyze the impact to their compliance and regulation requirement while being in the cloud. And when it comes to the encryption and key management, they were always mandatory. Back then in AWS, encryption was relatively common, but key management wasn't. For example, services like S3 and EBS offered encryption, but keys were managed by the service themselves. And as you know, exerting control over your encryption key ultimately determines who has access to what data. But trying to offer traditional key management in the cloud didn't make much sense. For instance, we couldn't ask each service team to operate a fleet of HSM just to do key management. Users are authenticated and authorized differently in the cloud. And HSM often requires special interfaces such as PKCS11 in order to perform cryptographic operations. So when we set out to create KMS, not only we had to design a secure system, but also one that's scalable in the cloud. And to help us guide with these design decisions, we came up with the 3 design tenets that we strictly adhere to when we're developing our service. These are security, durability, and availability. First and foremost, security is our top priority. It is not just our responsibility. By entrusting your data, encryption key, you're entrusting us with your sensitive data as well. Second, key must be durable as well. You rely on us to safeguard your keys from any natural disaster or event, so we have multiple redundancy in place to make sure that your keys are safeguarded. Third, availability. You depend on us to run your most critical workload, so your encryption key must be always available at all times. Underpinning everything is transparency. We are in business of earning your trust, and we knew from the start that earning your trust would be very difficult. People are used to hugging their encryption keys, and now we're telling them to put it into the cloud. So not only we have to design a secure and scalable system, but also one that's trustworthy. And to help us to do so, we do so by being transparent with how we built our service. For example, through sessions like these, we educate customers on how we operate and how we built our service. Third-party independent auditing helps ensure what we claim to do is rightfully done. And we follow standards like FIS 140-13 to ensure that our system meets the security requirement of government and international standard. So with these design philosophies in mind, we set out to create KMS. And back in November of 2014, we launched KMS. And with a handful of services such as S3, EBS, and RDS. And here's the actual blog post written by Jeff Barr himself 11 years ago. So where does KMS sit today? We're highly scalable to meet your needs. We process over 30 billions of requests, cryptographic requests every hour, which is unheard of in the HSM market today. And on top of that, we offer 5 nines of SLA to ensure your critical workload always stays up. KMS is convenient, and it's available in many AWS services through transparent server-side encryption, allowing you to enable encryption in your workload easily. And it is also available in some of the SaaS products, such as from vendors such as Salesforce and Atlassian, allowing you to bring your own KMS key and encrypt your own data, respectively, on these platforms. KMS is proven and trustworthy. We are FIPS 140-3 validated, independently audited, and we provide public documentation on how our system operates and how the process that we have behind the scene. So here's a high-level architecture view of the KMS service at the regional level. And as with most AWS services, we make a distinction between the control plane and the data plane. When you make an API request to the KMS regional endpoint, we first load balance using DNS amongst the different AZs. And within the AZs, we further load balance again among the front-end hosts, which process your authentication and authorization on your request itself. If the request requires HSM operation, we forward that to the backend HSM for cryptographic operation. Over the years of operating our service, one thing we learned from many customers is that customers have a different interpretation around what it means to be in control of their encryption keys. And this understanding usually comes from various framework, regulation, and compliance requirements. And we found that customers who are familiar with the concept of hardware abstraction have a more favorable view on the resource they own and control remotely. For example, you own an EC2 instance and S3 bucket within your own AWS account, and you control the access through the IAM policy. But going polar opposite, there are customers who believe that control means physical ownership, and when it comes to encryption keys, the keys must be within the HSM they control directly. The challenge that we face is that many of these requirements were written before the cloud computing became more common. While the security is an important factor, performance factors like scalability and availability are often treated in isolation and afterthought. Although we have seen over the years that customers have changed their view on this topic, time and time again, we still see customers who get just focused on just one aspect, missing the bigger picture and the actual risk that they're trying to mitigate from. The key message here is that while encryption keys are an important part of your data protection strategy, you need to think holistically about your overall security. Consider aspects like IAM policy, resource policy, SCP, RCP, and using concepts like segregation of duties to ensure that specific users and roles have access to your data. And the most importantly, your keys belongs to you. AWS has designed its core product and service to prevent anyone but yourself and those authorized by you from accessing your content. And this principle extends to KMS keys as well. And as you will see in a bit, this foundation of trust and control became the bedrock for addressing the evolving sovereignty need within our service. And from the KMS perspective, we focus on offering customers more ways to control their encryption keys while minimizing the impact to the customer experience. So a couple of years past, we launched KMS. We began hearing feedback from customers. Customers love how KMS is integrated with AWS services and super simple to enable encryption in their workload. But a small set of customers still held out, saying that they want to do their own key management. These are important keys, and the customers wanted extra assurance that their keys are well safeguarded. And so we launched Import Key, a feature that allows you to manage your own key within the HSM you control and provide us with a lease or a copy of the key within KMS to be used. The way it works is that you download the wrapping key from the KMS, wrap your secret key within the HSM that you own, and provide the wrapped secret key back to the KMS, and we will unwrap it and use it securely within our service. When we look into as to why customer did this, customers' reasons were quite straightforward. Many organizations have a dedicated team for managing encryption keys for years. These teams were responsible for creating and deploying keys throughout their organization, and they just viewed cloud as another location to deploy their keys into. And they were comfortable with the existing process and approach that they already had. But the challenge here is that cloud is designed to be highly agile and adaptable, and having to wait for a single team to deploy something goes against this principle. So what are some common misses when customers did this? They quickly learned that key rotation became a nightmare scenario. When you rotate the key outside, before you can rotate it, you need to decrypt all the data that was dependent on the old key and re-encrypt it under the new key. And there's a tremendous amount of work, effort, cost, and risk involved for everyone involved. In native KMS, we solved this elegantly by offering automatic key rotation, where you just set a time frame from 30 days to 7 years, and we'll rotate the key for you. Another pitfall that customers realized with importing a key is the management itself. If you're importing a single key, that's not a big deal. It's relatively simple to do. But what if you're dealing with hundreds of keys or even thousands of keys? Now you need to independently upload them and configure their use within AWS. And that is a lot of operational headache that most customer doesn't want to deal with either. So when should you be doing this? One good use case is asymmetric key. So if you have a signing use case, such as co-signing or signing a certificate, and you want to bring the same workload into AWS, you can upload the private key into KMS securely using this feature and bring the entire workload into AWS. Another use case is if you want to control your own durability of the key itself. While KMS offers 11 nines of durability, if you feel safer knowing that you have a copy of your encryption key sitting beside you in the HSM, this is one way to achieve that objective. 2 years after we launched the import key feature, we started hearing from another group of customers. This time, not only they want to manage the key themselves, they want to manage the entire HSM as well. And we launched Custom Key Store backed by Cloud HSM. A custom key store is a feature that allows you to bring external key manager and connect it to the KMS. This allows you to own the cryptographic material and control the cryptographic operation within the HSM that you control. The way it works is that your keys are actually hosted inside the Cloud HSM instance, and when the call is made to the KMS, we simply relay that call back to the Cloud HSM instance. Now, initially, we couldn't really understand why customers actually wanted this. After all, we spent significant energy developing highly secure, highly scalable key management service, yet customers still wanted to manage their own HSM for some reason. And when we dive deeper as to why, it all stemmed from customers' misconception around multi-tenancy. They were afraid of things like the noisy neighborhood problem, where action of one tenant would affect another. And to avoid this kind of issue from happening, they would rather just pay extra cost to get their own dedicated hardware instance. Another concern that we heard was, what if KMS accidentally leak a key or accidentally intermingles a key from one customer to another? In this kind of situation, isn't it better to have an isolated, independent instance to prevent this kind of from happening? And my answer here is no. And you'll see this in a bit because KMS is designed such that this cannot simply happen. But nonetheless, customers still choose to use Custom Key Store and Cloud HSM to mitigate the risks that are unfounded. So what went wrong when customers did this? The main challenge here is the scalability and availability issues. Instead of relying on us to scale for you, now you need to manage your own capacity, set up your infrastructure, set up your networking, and that's a tremendous amount of work and effort on your side to manage that all. And that comes with additional cost overhead that most customers often overlook. This kind of setup usually works for low throughput workload, such as attaching an AWS instance or starting an RDS cluster. But anything high throughput, such as analytic or data processing job, will often fail because your data requires constant access to the key itself, and the custom key store becomes a choke point at this point. So when does it actually make sense to use custom key store and Cloud HSM? Based on our experience, it makes the most sense for the initial migration itself. If you don't have the resource to refactor or re-architecture your application, then custom key store allows you to simply lift and shift your existing workload into AWS without much effort. So we've been talking about custom key store and Cloud HSM for a while. And I think this is a good time to talk about our own HSM, the KMS HSM itself. Since day one, we have been investing and developing our own hardware. We own the entire stack, from the hardware, firmware, all the way through the application code itself. And throughout the development process, we submit our system for FIPS evaluation. The FIPS standard and the cryptographic module validation program is overseen by NIST, or National Institute of Standard and Technology, which is a US government agency. The FIPS standard is important because it sets the benchmark for cryptographic security, helps prevent weak implementation, and widely trusted by many governments and industry alike. This program itself has evolved over the years. Recently, it was updated to FIPS 140-3, incorporating modern security requirements and aligning with the international standard. And we reached FIPS 140-3, security level 3, back in May of 2023. So what happens inside the KMS HSM? What makes our HSM a little unique is that it has no concept of tenancy built into the place. It's a stateless machine with no persistent state kept inside, meaning we don't store customers' key permanently in the HSM or partition the hardware in any way per customer basis. You can kind of think of it like a black box where input and output behavior is predefined like a mathematical function. Each request is load balanced and handled independently from one another. And this is done at tremendous speed and scale, processing over millions of requests per second over thousands of HSM fleets. When handling your requests, your KMS key always remains in encrypted format. If and only if the key must be used, we send encrypted copy of your key into the memory of the HSM, decrypted it within the memory, operation is performed, then the key is quickly flushed out and deleted from the memory itself, and the payload is returned back to the requester. Every encrypted data or ciphertext produced by KMS has a key ID embedded within it as well. And this helps ensures the integrity of the ciphertext itself, and also prevents your key cannot be used without proper authentication and authorization for that ciphertext as well. Now that we covered what the KMS HSM is, let's dive deeper into how we protect and secure the software running on our HSM. And this is a really dense slide, so let's break it down one point at a time. When the HSM host is loaded with the software serving customer requests, it is in operational mode. When it's operational mode, there is zero operator access, no software update can be made, and customers' keys are provisioned within the memories only. It is simply impossible for an operator to access the HSM at this time, as there is no SSH, no private API, or no debugging mechanism whatsoever. And as I explained earlier, every input and output is predefined, and only the attested KMS front-end system can make a request to our HSM. When the host reboots itself or initializes for the first time, it enters non-operational state. One thing to note is that our entire software stack runs in memory, as there is no persistent disk within the HSM itself. So when HSM loses power or reboots itself, the software, along with the key itself, is all quickly flushed out from the memory itself. And once we have this blank state, this is the only time when our operator can upload a new version of the software into the HSM, and that requires rigorous code review and multi-party approval process, which is a two-step process overseen by quorum of operators to ensure that no one can introduce unapproved change into our system. Now you might be wondering yourself, how do we actually validate what we claim to do? And this is where the FIPS validation comes into play. Each time we make modification to our software, we submit it to the FIPS evaluation for verification, ensuring that we're not deviating away from the standard itself. In addition, there are SOC control, which help ensure that our processes are always followed. And I have highlighted one here, the SOC 1 Control 414, which says the firmware is always validated or in the process of being validated at all time. There are many more controls, all designed to give you transparency and assurance behind our process. And I highly encourage you to take a look at our independent report, which can be found in the AWS artifact. Coming back to the KMS architecture, last and least, we have something called External Key Store, or XKS. The way XKS works similar to the custom key store, but this time we're introducing a proxy in between KMS and your on-premise HSM. And all the cryptographic operation happens inside your on-premise HSM itself. Now, we truly believe KMS is the most secure, most durable, and most highly available place to safeguard your key. Nonetheless, sometimes you're put in a difficult situation where you're working with a stakeholder or requirement that is absolutely hard to change. While XKS is not an optimal solution, it provides you a way out of this trap and gives you a way path forward. When we dive deeper as to why a customer wanted XKS, one of the misconceptions that we found was the idea around ciphertext portability, or ability to take encrypted data and decrypt it elsewhere outside of AWS. For example, in case of serious political event or natural disaster, the idea is that you can take a copy of your backup data and decrypt it locally using the key that you've been holding on to. But the problem with this idea is that there's actually no way for you to download the encrypted data as is from the AWS services. For example, when you make a GET call to the S3, everything is decrypted on the server side and provided back to you over a secure transported channel in a plain text format. So holding onto your keys give you no additional assurance or risk mitigation whatsoever for this kind of scenario. Another reason we heard was ability to take out your key or yank out your key, preventing anyone, including AWS itself, from decrypting your data. But again, this reasoning is flawed because there are multiple ways you can achieve this objective within AWS. And looking at the KMS only, you can do so by importing a key and taking it out later on when needed. Looking at the challenges similar to the custom key store, we have the same scalability and availability issues. But what makes XKS even worse is that now you're introducing a single point of failure into your workload. If proxy goes down, or if your on-premise HSM goes down, your entire workload will go down as well. Not to mention every workload you have within AWS will need to make a network call over the internet to reach your on-premise HSM, which introduces latency and instability into your workload as well. So when should you use it? And my frank answer is ideally never. However, if you're working with a demanding customer where you're put in a situation where unreasonable demands are pushed upon you, then as a workaround, XKS offers you a way out of this trap and gives you a solution forward. So here's an example of how external key store architecture can look like. Everything to the right side of the KMS in a green box belongs to you that you control, meaning you need to manage the VPC and the instance that hosts the proxy itself, the link between the proxy and your on-premise HSM, and your on-premise HSM itself as well. So taking a step back, we start out by solving simple customer need. Customer needed encryption keys and needed a way to control their encryption key while being in the cloud. As more and more customers still start to migrate their workload into AWS, we start running into customers with different expectations around what it means to be in control of their encryption key. Some were comfortable with the cloud-native approach, while some others meant that physical ownership of the key is crucial. And to help bridge this gap, we had to innovate, and we had to come up with a technical solution that meets customers' need. But we understand that every customer has a different requirement and comfort level, hence we provide options. But it's important to understand what these options bring and challenges that they have before pursuing them. I've been talking most exclusively around how you can use encryption to control access to your data, and your key is a gatekeeper in all of this. Now let's apply this knowledge to solve a use case that's hard for most customers, the digital sovereignty use cases.
Hello. Everyone can hear me? Just hands up, just make sure good audio is functioning. So digital sovereignty use cases. First, I want to talk about what the term digital sovereignty means, because it may be something a bit different to what you may understand, data sovereignty, data resiliency and residency sort of points. Digital sovereignty is a term that we have coined at AWS to help cover all of these topics, because these four areas tend to be what customers are most concerned about when they talk about digital sovereignty. They worry about country of residence, where is my data going to be stored, where is it going to be processed, are there any third parties involved in that processing. Second area is around operator access restriction. They want to know who can go into a data center, plug into the back of one of our racks and have a look at something, or who can, in the service teams, can access our data and when they do that. Resiliency and survivability, and this goes a bit beyond the usual stuff of a natural disaster, but as we saw a couple of years ago with the Ukraine, when they moved a lot of their public sector workloads into AWS Commercial Cloud, it can deal with situations where there's kinetic warfare, where entire industries or entire countries are failing. Because sovereignty usually refers to country-level law or regional law. And fourth item is independence and transparency. And this is where customers want to be able to say that there's no dependency on US East 1, which some of you may have had some challenges with in the last month or so. They want to make sure the technology stacks are truly independent. They want to have special requirements, such as only citizens of certain countries or residents of certain countries are allowed to operate these environments. So some of these things, all these add together to sort of make the sort of picture of how customers understand digital sovereignty. And also this varies by country, by industry. So it's a very complex field. And sometimes within the same country, multiple laws dealing with different aspects of sovereignty in different situations. So three broad categories of controls that we provide, some on our side of the shared responsibility model, and some on your side that you configure and control. These three categories are technical measures. Using KMS is a really good technical measure. Protecting your keys that are stored in KMS with resource policies is a technical measure. Protecting access to the KMS API with identity and access management policies is a technical measure. So role-based access control to keys, backups and logging. These are all technical control examples. Organizational measures, such as you'll have policies. We only use these crypto algorithms. We keep data for this retention period. Whether it be from external forces, such as laws or regulations that require you to set those values, or something your organization sets for itself, for its own purposes. Standard operating procedure documentation, hiring procedures, vetting staff and people from what country they have, what their background is, before you employ them. These are all organizational controls that we employ. We security clear a lot of our employees. We do background checks on our employees, so do you. And contractual measures. This is the not so fun stuff, the service level agreements. Who's read the service terms for AWS extensively online? Hands up. Everyone read the service terms? All right, nope, that's not even one hand. Okay, interesting. In-user license agreements, third-party supplier assessments, all that sort of good stuff, and independent audits. That's in your contractual controls piece, the bits of paper that lawyers can go and refer to should things go wrong. So, sovereignty, technical measures, what do we have that is, well, how does KMS support digital sovereignty based on those requirements of particularly operator access, particularly residency and control? Let's dive a little deeper in that. So data sovereignty and encryption combined talk about control of location. Perhaps it is enough of a control to say that my data is stored and processed in Frankfurt in Europe. Hands up, who's actually here from Europe out of curiosity in the audience? Okay, we've got a few people. Yep, me too. Well, London technically, not part of Europe, but that's a different story. So the aspect of location of data is very important. Now, we already have contractual commitments in our data processing addendum that say that when you put data in a particular region, it will stay there unless particular circumstances occur. And that KMS is a regional service. So we talked a little bit earlier about control plane and data plane. The KMS service, when you create a key, it is available in the region, and therefore it is highly available and highly resilient because we look after that stuff on our side of the shared responsibility model. And keys don't transfer outside of a region unless you say so. Even multi-region keys, technically there is no point where the keys are available in plain text outside of a KMS HSM, even though you've got multi-region keys. So they're always secure within the KMS environment. Now, by protecting the key used to perform encryption, we can ensure that no one, even if they have access to the ciphertext, can get the plain text. Remember, crypto is a triad of three things: plain text, ciphertext, and a key. You need two of those things to solve the third part of the equation. Even if a bad actor gets your ciphertext, there's no way to extract a key from KMS. Therefore, they cannot complete that critical step of getting to plain text. And if we accept the truth that KMS is audited, our HSMs are reviewed and independently attested, there is no engineering possibility of extracting a key in plain text from that service. If you look at, moving on. Oh, button's not working. Come on, button. There we go. So let's start through an example. We're going to use threat. Who's done threat modeling? Hands up who's done threat modeling. Familiar with threat grammar? Okay. Threat composer, anyone used that before? Hand up. Okay. As a side, we do have a threat modeling tool that's so good. We used it internally and then we open sourced it called Threat Composer, available on GitHub. But creating threats with particular grammar helps structure your threat so that you're focusing on the issues that are really important, as opposed to sometimes people waffle on when they talk about threats, particularly when it comes to state-sponsored actors. So the threat actor in our case here is any unauthorized third party. It could be a government entity of a government you don't want reading your data. It could be a competitor. We'll cover internal actors in the next threat model, but any unauthorized third party, and we'll assume external in this particular case, with access to your crypto keys, remember the crypto triad, they have to have two of those three things. Can they decrypt your data? Potentially they can, resulting in reduced confidentiality of the encrypted data. So this is this threat grammar version of it: actor, prerequisites, and the thing they can do. Now, we have some assumptions for this particular threat. The unauthorized party has access to your encrypted data. So now they've got two pieces of the crypto triad. They may have acquired that data through following some due legal process, or they may have stolen it, intercepted it in some way. So there's various ways they might get hold of your crypto text. The mitigation, in simple terms, is use KMS. It's very simple. You can't get the key out of it. Not even AWS employees can extract the keys for a third party to go away and take that crypto text and turn it back into plain text. And focusing particularly on the Cloud Act, which is published in 2018, we have a report from IDC, an independent report. Even if the encrypted data is transferred to a law enforcement body via a due process with all the right warrants and all the right courts and judges approving it, including possibly yourselves as customers, there's no requirement under that to give away the key to decrypt that encrypted data. They have to come to you as a customer, and that allows you as a customer to maintain agency over your data. There is no leak here because encrypted data is zeros and ones, it is noise. You can't turn it back into plain text in a reasonable time with today's technology. Maybe the future technology in 1,000 years might be able to say something with it, but not today. So the essential thing is this is what KMS does for you. Trust KMS, the keys don't escape. Encrypt your data with it, and particularly customer managed keys. Now, let's adjust our threat position a little bit. The malicious actor or process is inside your organization now. It may be, perhaps it's you use a managed services company based in a different country where the laws around data management and key management are different than in your own country of operations or your home country of operations. It may be that you are employing developers from either internally or externally to write code for you, putting code in your repositories. And due to some flaw in your code static analysis scanning or code threat scanning, a piece of malicious code has made its way through in your pipeline to run on an EC2 instance or perhaps in a Lambda functional container. Now, this threat actor, be it a human or a process, has now got a policy that it can use to access keys. And this particularly gives it the ability to do things like we've seen ransomware attacks where malicious code was injected into Lambda functions and EC2 services that customers had. And then the key was changed, used to decrypt and then re-encrypt for a different key outside of AWS. This is a nasty attack, a form of ransomware attack. So this does happen. And with that user, that process or that developer has the ability to access KMS and manage keys and get access to your ciphertext, then it can re-encrypt it or decrypt it and exfiltrate that data in various ways. So very much on your side of the shared responsibility model at this point. Assumptions, the eternal actor must have AWS credentials. Everything relies on a SIG v4 signed request, access key, secret key, session key, whether it be a server, a container, a Lambda function, or a human being. And it must have a role with permissions to the KMS service to run crypto calls as a crypto user for those particular keys. So these are our assumptions. And before we cover the mitigations, let's do a quick micro refresh. Hands up everyone who's totally comfortable with SIG v4 signing. One hand, okay. I cannot emphasize this enough. Become familiar with it. If you've ever done Python development, you've used the Boto3 library, put it in debug mode and see what happens. See how keys are used. That access key and secret key is critical. And that's why we tell you so many times as customers, be very careful not to commit those keys to accidentally put them in a GitHub repository or somewhere. This is a bad thing. That's a different talk. But yeah, you don't want to do that. So we know there is a user. It could be a process, could be a human. We know there's a bucket where data is going to be stored, and we want to maintain the sovereignty of this data. We know there's front-end APIs to the KMS service itself and where the KMS key lives. So what protects our data and our keys? SIG v4 sign request. That's the essential, the real perimeter of cloud is that authentication and authorization piece. It's not your firewalls, and to a lesser extent your firewalls. We know that AWS services generally support TLS 1.3 with post-quantum encryption algorithms available in many of the services already. 1.2 is still supported. We recommend you don't use 1.2. So we know that the traffic is encrypted as it passes down through these services. We know that there is an IAM policy that allows you to make calls to the KMS service, a regional service. Remember that. We know there is an S3 bucket policy, a resource policy assigned to a particular bucket. And we have KMS key policies as well that determine who the crypto admin users will be and who the crypto users will be. And those two types of account are common to maybe on-premises cloud HSMs or on-premises HSMs, not cloud HSMs, that you've used in previous times. And additionally to that, this is an optional one. You may not use AWS organizations, but if you do, there are service control policies that can be applied across multiple accounts and organization units, and additional resource control policies to control what principal can do what with a key and with the data as well, separately. So all of these things combine to get to our mitigation example here, which is where we need to make sure that the encryption key cannot be misused, because we know the ciphertext is escaped, that can be pulled up under an official warrant, that can actually be taken away. but we know the key can't. So how do we protect a key from these internal actors? Well, this first one here, we can see that the principal for the actual encryption, decrypt, encrypt, and generate data key is an EC2 role. So our example is we're using an EC2-based application that's running in an EC2 instance to actually make the calls to KMS to decrypt data and process it in some way. So this is our effective, our crypto user type account. So this makes sure that only that principal can do these operations, which is essentially generate data keys that are used for envelope encryption. Hands up who understands envelope encryption in its entire... okay, we've got a few more there, okay. Envelope encryption is pretty cool. If you don't know what it is, there are lots of talks and blogs on that particular one about how to go into depth with that. Now, the other aspect of this is we've covered crypto users, we haven't covered crypto admin. Now, that's a second policy statement there where we're saying only this particular role is allowed to do puts, updates, and revokes in the KMS service itself. So that's essentially the crypto admin role that does key management, separation of duty, least privilege. These are critical things in the KMS key policy itself. Now, another thing to think about this in KMS key policies is that they enforce explicit allows only, right? What this means is if the principal is not in the policy, it can't use the key. That includes the root user in your account. So when you set up policies for key admin or crypto admin users, make sure they really work. Because once you've locked root out, that's bye-bye key. So test your policies, check them. In my case, I love Kero CLI. It does a really good job of doing least privilege policies and optimizing policies. I've seen an SCP policy being reduced by 78%, and it still had the same effective controls on data. It's quite very, very clever. So those are the things there. So in summary, what this policy does is it locks the key usage and key management down to very specific principles. But that's only part of the picture, because the other part of this mitigation is the resource-based policy in S3 itself. Now, we've done and this is a defense in depth type implementation in this case. So we can still do denies unless it's a particular role writing to a particular bucket. We could add denies if it doesn't come through a particular VPC endpoint. So you can adding lots and lots of depth there via networking, via the role that is used. You can even add one now for a new feature where you can do attested signed EC2 images, much like you used to do with Nitro enclaves. So now the usage of a bucket or a key can actually be locked down to, does this signed EC2 AMI image allowed to use it, or container. In this particular case here, what I want to draw your attention to is that we've actually said, okay, not only does it have to be a particular role from a particular VPC, i.e. an EC2 instance in this case, but it can only use a particular key to write objects to that bucket. So it's absolute control of the key. This helps facilitate against preventing that very type of ransomware attack we talked about earlier. And particularly this is a resource in the S3 bucket itself. So even if the attacker has KMS and they have a bunch of other permissions, if they don't have permission to the bucket and the bucket policy, they can't steal or otherwise reduce your availability to use your data. So explicit denies in this particular case create a security invariant, i.e. it's something that you can very quickly test and validate. So these are super useful in this case. Now, that's technical measures. There are two more types. And this is where European Sovereign Cloud comes into its own, because it's important to note, European Sovereign Cloud is a partition. Partitions are not a new thing. We have partitions, and that's a GovCloud, that's a partition. AWS China, that's a partition. There are also partitions for particular customers with super special needs who want to have a slightly different slant on the shared responsibility model called Amazon Dedicated Cloud. I'm not going to ask you if you have a customer who uses ADC here, because you're not really supposed to say if you're a customer of ADC. But anyway, I'm in the British Army, what can I say? So technical controls, we've talked about those. Let's talk about the organizational and contractual controls, because this is where European Sovereign Cloud is different. So we wanted to make sure that there are other sovereign cloud options available to you in the European marketplace. One of our competitors, OVH, does a very good product. Other competitors do as well. But in our view, it's not the AWS experience that you as customers expect. The number of services, the availability of features. So when we build a sovereign cloud, we want it to be exactly like the cloud and commercial partition that you're used to. The same services, the same reliability and availability. In the case of the European Sovereign Cloud, it's only one region today. That doesn't mean more regions aren't on the way. And remembering a region is a unit of availability. They are highly available in terms of data centers, network compute, storage. They meet those many nines SLAs that are required. So the fact it's a single region isn't really a big deal. Now we know customers, as I said, they want to adopt sovereign cloud, but they want all the features. They don't want the compromise. And that's why, in our view, to build a cloud that can do that, you need to spend a little bit under $8 billion to achieve it. Again, when thinking about how competitors do sovereign cloud in Europe, think about how much have they spent. For Amazon, for us, it's $8 billion. That's or euros, I should say, to get something that does what customers need. So it's going to launch before the end of the year. That gives you about 3 weeks. So we won't do a sweepstake on which week it's going to be. But it's a serious investment to make sure that European customers can do what they want to do in terms of organizational controls. Now, what are some of these organizational and contractual controls? So we commit to any region. You put your data there, it stays there. European Sovereign Cloud is the same, but it is a different cloud. I'll talk about it a bit more in the contractual side, but if you create an account in European Sovereign Cloud and an access key and a secret key, it will not work in commercial cloud. It's a different root of trust. It's a different partition. It's a different IAM. If you want to move data between European Sovereign Cloud and some other region in commercial, you need to choose to do that via the internet or via APIs that you create yourselves or by using something like snowmobiles or snowballs or something like that. So the European Sovereign Cloud, it is separate root of trust, separate region in terms of infrastructure, network compute storage, separate partition. And these are very important things to point out because it's not a matter of just like saying, I'm going to replicate the bucket from commercial to ESC. You can't do that. You need an intermediate process. There are also extra controls that are placed on customer metadata versus customer content. So customer metadata is things like the name of an S3 bucket, to use an example. Customer content is all the zeros and ones that create the object that are put into the bucket. The name of the file, the name of the bucket, the name of policies and things that you use are metadata. They are not necessarily invisible to service teams. The zeros and ones that are encrypted that make up the object that's in the bucket are customer content. That's the best way to think about it. And the S3 example is a very good one, a clear one to try and talk about in that space. So point being is that metadata is not transferred out of region either. In commercial regions, metadata can be visible in other regions to other operations and services teams. So this covers part of that operational access thing we talked about earlier. Now, physically independent, multiple availability zones, all powered by Nitro architecture. So there's a important point there is that the technology stack does not change. The S3 service in the European Sovereign Cloud has the same API as the S3 service in any commercial region, or perhaps GovCloud as well, though sometimes there's not feature parity in those particular partitions. So these are key things, and separate in-region billing and systems. You have to create a new account in European Sovereign Cloud, new billing. If you already have an enterprise agreement, you may need to revise that because it's now a separate agreement because it's separate sovereign clouds. That's why. And the offshoot of that is that when you're thinking about it from your side of the shared responsibility model, if you want to have stand up a stack in European Sovereign Cloud and have a stack in commercial cloud, and you want them to be more or less the same because the services are more or less the same between the regions, if we've gone to the bother of separating out a sovereign cloud, do you really want to be using one Terraform stack and one operations team pushing stacks to both environments? Does that still meet sovereignty requirements? Again, this will be driven by your customers' needs. You may have to do what we've done, which is to stand up proper operational autonomy. And this is another organizational control. So for European Sovereign Cloud, it's not just a separate environment and a separate partition, it's separate people and separate processes based in the state of Brandenburg in Germany. So when whatever law applies is European law to the use of data in that region. Separate management chains, qualified European Sovereign Cloud staff who must be EU resident, and in the future will also only be EU citizens available to operate that environment on our side of the shared responsibility model. And this opens the question, if you're a multinational organisation that plans on doing business in Europe or needs that European sovereignty, do you need to set up your own sovereign operations rather than using a common operations team or even offshoring type operations when you're actually running workloads in sovereign cloud? These are questions you need to think about on your side of the shared responsibility model. But we would suggest you probably do, because that's what we've done. That's why it costs $8 billion. Cost of people, cost of power, and amongst other things. So this is how the residents located in the EU and the full control over operations and support. This is how we can ensure that we can meet European requirements and make sure that there's a separation so that things that are running in European Sovereign Cloud do not have dependencies on commercial clouds or other partitions. Moving on. And this is one that comes up a lot with European customers. For American customers, maybe not quite so much, but it depends again on your industry and where you are based, and to a large extent, who your customers are. There will always be talk about law enforcement access requests. We commit to your data staying in region unless required to be looked at or moved around as part of maintaining and operating the service, or in compliance with a subpoena from a valid court and from a valid legal jurisdiction. So as part of the technical measures around how we approach these law enforcement access requests, again, technical, organisational and legal and contractual measures that we enforce as part of European Sovereign Cloud. The technical measures are KMS. You can't pull keys out of that. The key stays there. Even if German law enforcement required you to give up your data for some reason, it's encrypted data, they still have to come to you for the key. So that integrity of control over your data is maintained, regardless of where that request comes from. All computing in Sovereign Cloud is based on the Nitro system. We know the Nitro system is independently attested and proven to say there is no operator access to guest operating system images, i.e. EC2, running inside the Nitro hypervisor. There's no console port to go into, like used to do in the old days, go into the data center, reboot things, usually Windows servers, to make sure that they'd keep working. Just can't do it. None for us in our data centers, none for you, none for any other external entity that might go into our data center, which we generally don't tell people where they are and we don't let them in, even if they ask. Operational measures, we only have AWS European qualified staff running AWS European Sovereign Cloud. That is EU residents. In the short term, in the longer term, it'll be only EU citizens. So there's an absolute connection between the people running it on our side of the SRN and where you want to run your workloads. It's inviolate and it's contractually proved. They are Europe first employees, from the managing director level all the way down to all parts of the organisation. And there are many subunits within the organisation established in the state of Brandenburg to make sure that control lives in Europe. And legal and contractual measures. For example, one thing we have in the European Sovereign Cloud is each and every law enforcement access request is considered individually. It's not like there's they go in batches or something, or like we've had 5 requests from the same entity, we're going to load them all up in the same job. No, every single request is treated independently, reviewed by our legal, and then we talk to you about it and your legal about it, if we are able to. So AWS we commit to make every reasonable effort to ensure that you, the customer, are the people that have to interact with law enforcement where data access requests are coming along, because we don't want to, in a certain extent. So that's part of the contractual organisational controls we have in that space. And that more or less brings us to the end of the thing.
All right, thank you, Sam. So we talked a lot in the last hour what it means to be in control of your encryption keys, and what it means to how it relates to the digital sovereignty need and the European Sovereign Cloud. And you might be asking yourself, where do you actually go from here? So if you have earned your trust and you believe the KMS is the right place to safeguard your keys, then great, our job is almost done. However, whether you're convinced or not, we still recommend you to do your due diligence, read upon our documentation, read upon our audit reports, and run experiments. And tell us what we can be doing to earn your trust even more. If there's something that's not explained well, you should ask us to clarify. Only way for us to improve ourselves to hear from you on what we can be doing better. And thank you very much for attending our session. And please fill out the survey as you go out. Thank you.